Hello all, welcome to this channel cfdbaba. Here we simulate CFD cases using ANSYS Workbench Fluent. This is part 2 of heat transfer and fluid flow analysis in shell and tube heat exchanger. In the previous video, I have already demonstrated how you can create a geometry inside the design modeler in ANSYS Workbench. Today, we will simulate the geometry that we have created in the previous video. Do not worry if you do not have time to create the geometry. I will provide the geometry in the link in the description below. You can download the geometry and directly start doing the simulation. Drag in the Fluid Flow Fluent tab. Right-click on Geometry. Select Import Geometry. Select the heat exchanger. Right-click and select Edit Geometry in Design Modeler. This will open the geometry inside Design Modeler. Click on Generate. This is the geometry of a simple single pipe shell and tube heat exchanger. It contains 4 parts: shell wall, shell domain, the tube wall, and the tube domain. The shell wall should be solid. The tube wall should be solid. The tube domain should be fluid. And the shell domain should also be fluid. Make sure you have assigned the correct solid and fluid properties to the geometry parts. Once the correct properties have been assigned, select all the bodies, right-click and form a new part. This will ensure that we get a conformal mesh in the meshing section of ANSYS Workbench. Close the Design Modeler. Right-click on Mesh, click on Edit. So our geometry has been imported inside the meshing module. Click on Mesh, click on Generate Mesh. We will use the default mesh settings for generating the mesh. As you can see, the mesh is fine at the inlet and outlet face of the shell. Also, you can see that the mesh is conformal between the solid and fluid domains. Conformal mesh means that each node on the solid as well as fluid domain is connected at the point of intersection between the solids and the fluids. This is known as conformal mesh. Conformal mesh is required to simulate conjugate heat transfer so that we can calculate the convection as well as conduction effects. Now we need to name the parts in our geometry so that we can use them in the boundary conditions. Select the face filter. Select the top face. Press N. This will open the Selection Name tab. Name it as Hot Inlet. Select the bottom face. Name it as Hot Outlet. Select the face on the right hand side of the shell and tube heat exchanger. Press N. Name this as Cold Inlet. We are going to simulate for a counterflow heat exchanger. Counterflow means that if the hot fluid is entering from the positive x direction, then the cold fluid will enter from the negative x direction. Thus we have named the hot inlet, hot outlet, cold inlet, and this face will be the cold outlet. Press N and name it. Press N and name it as cold outlet. Press OK. Now we need to name the walls and the fluid domains. Select the volume selection filter. Select the shell wall, press N. Name it as shell wall. Select the tube wall, press N. Name it as tube wall. Select the fluid domain inside the shell, press N. Name it as shell fluid domain. Select the fluid domain inside the tube, press N. Name it as tube fluid domain. Press Enter. Now we have all the necessary boundaries to simulate the flow through this heat exchanger. Right-click on Mesh, click on Update. This will translate the mesh to Fluent successfully. Close the Meshing tab. Right-click on Setup, click on Edit. Use the double precision option. I will use parallel computing. I will select 4 processes. These are the number of cores that your system has. Press OK. Once the geometry is imported along with the mesh, we will start applying the boundary conditions. We will simulate a steady state case. Turn on the gravity so that the fluid knows where to go after its temperature increases. Enter the gravity as minus 9.81 in the Y direction. Double-click on Models. We need to turn on the energy model so that we can calculate for the temperatures. Always turn on the energy model when you need to solve for the temperatures. Double-click on Viscous Laminar. We will use K-epsilon turbulence model with realizable and scalable wall functions. Click on OK. Next, we need to assign the materials. Select the material air and click on Create/Edit. We need to import water as our material, which will be the fluid. Click on Fluent Base. Scroll down to the bottom. You will find the water liquid. Click on Copy. Click on Close. Click on Close. Also, we need the solid to be something else than aluminium. Click on Create Edit. Go in the Fluent database. Select the material type as solid. Here we will use copper. Click on Copy. Click on Close. Again click on Close. Now we have imported water and copper, which will be used to set up the materials for solid and fluid domains. Next, we will assign these materials in cell zone conditions. Select the shell fluid domain. Click on Edit. Select the material as water. Click on OK. Select the tube fluid domain. Click on Edit. Again, select the material as water. Click on OK. And for the walls that are the solid domains, we need to specify the material as copper. Click on OK. For the tube wall, again select the material as copper. Click on OK. Once the cell zone conditions have been assigned, we will assign the boundary conditions. We only need to assign the inlet boundary conditions. Click on Hot Inlet, click on Edit. Select the velocity as 1 meter per second. Go in Thermal tab and select the temperature as 90 degrees Celsius, but the unit being used here is Kelvin. Let's change the unit first. Click on Units. Scroll down until you find the temperature and select Celsius as the unit for temperature. Click on Close. Again, we will click on Edit and now select the velocity as 1 and the temperature can be selected as 90 degrees Celsius. Click on OK. Now we need to specify the velocity and temperature at cold inlet. Click on Edit. Select the velocity as 1 meters per second. Go in Thermal tab and select the temperature something cold as 15 degrees Celsius. Click on OK. Now the heat transfer will take place between water at 90 degrees Celsius and the second water that is at 15 degrees Celsius. Make sure that the type for inlets is velocity inlet and the type for outlets is the pressure outlet. Once the boundary conditions have been set up, go in the operating conditions. Here, we need to check the specified operating density so that the hydrodynamic pressure will be considered. Click on OK. Double-click on Methods. We will use the coupled method with second order upwind scheme. Double-click on Initialization. We will use the hybrid initialization. Click on Initialize. This will start the initialization. Once the initialization has been completed, double-click on Run Calculations. Enter the number of iterations as 100. Click on Calculate. This will display the residual graph on our screen. Residual graph is nothing but the difference between the actual values and the calculated values. We want the difference between them as minimum as possible. Hence, residuals of order 10 raised to minus 3 are preferred in most of the simulations. After the iterations have been done, you will get a calculation complete message. Click on OK. The 100 iterations have been done. Let's view the results in the Results tab. Right-click on Results, click on Edit. This will open CFD post. We need to create a location that is plane. Click on OK. We will create the plane in the XY direction. Click on Apply. This will create a plane at the midsection of our geometry. Let's visualize the velocity on this plane. Click on Contour button. Click on OK. Select the location as Plane 1. Click on Apply. This will show us the pressure distribution in the heat exchanger. Click on Velocity. Click on Apply. Here you can see that the flow is coming in and going out from the inlets and outlets respectively. Select the number of contours to 110. Click on Apply. You will be able to visualize more smoother contours. Switch off the Plane 1 view. We can also visualize the temperature. Select the variable as temperature. Click on Apply. Select the range as local. Here you can clearly see that the cold fluid is coming in through the inlet and going out as heated fluid through the outlet of the tube, whereas hot fluid is coming in through the inlet of the shell and leaving the shell as a more colder fluid. This shows us the heat transfer phenomenon between the hot and the cold fluid. We can also view the vectors inside the fluid domain. To view the vectors, switch off the contour button. Click on the Vectors button. Click on OK. Select the location as plane 1. Click on Apply. This will show you the direction of the flow. You can see that the flow is coming in through the inlet and going in through the outlet. This is the inlet for our shell, and this is the outlet of our shell. You can see that the fluid is going out. This means that the boundary conditions have been correctly implemented. In the tube, you can see that the fluid is entering from the right-hand side, and it is leaving the tube from the left-hand side. This ensures that all the fluid directions are correct. We can view the temperature vectors as well. Go in Color, select the variable and select the variable as temperature. Click on Local. Press Apply. You can see that the hot fluid coming in through the shell inlet has been cooled down as it has reached up to the shell outlet. We can also view the streamlines. Switch off the vectors. Click on the Streamlines button. Click on OK. We want to view the streamlines on plane 1. Select the direction as forward and backward. Click on Apply. This will show you the streamline flow, but there are too few streamlines to visualize anything meaningful. Let's increase the number of points to 250. Click on Apply. This will show you the flow that is coming in through the shell and going out through the shell, as well as the flow coming in through the tube and going out through the tube. Let's view the temperature streamlines. Select the variable and then select temperature. Select the range as local. Click on Apply. Here you can see that the hot fluid is flowing over the cold fluid, and hence the heat transfer takes place between the hot fluid and the cold fluid through the wall of the tube. Because both the fluids are not in direct contact with each other, there is a wall in between them. This is called simulation of conjugate heat transfer using ANSYS Fluent. If you want to view the temperature difference more clearly, you can view that by using user-specified values. Switch off the streamlines, click on Contour button. Here, double-click on Contour and select the range as user-specified. Switch the units to Kelvin. Here, we will select the minimum of 15 and maximum of 20. Click on Apply. Now you will be clearly able to visualize how the cold fluid is coming in through the inlet with the blue color, but as it is going along the length of the shell, it is getting heated up and you can see the yellow color at the outlet. Similarly, if we select the range from 80 degrees to 90 degrees, press on Apply, you can see the temperature variation inside the shell fluid volume. You can see that the fluid entering the shell is hot that is the red color. You can view the corresponding colors and their values from the legend view. You can see that hot fluid is entering the shell and leaving it as somewhat a colder fluid. This shows us that the heat transfer is actually taking place between the shell and the tube fluid volumes. So this is how we simulate heat transfer and fluid flow through shell and pipe heat exchanger. If you have liked this video, please comment down below your favorite part and don't forget to share this video with your fellow CFD colleagues. We will meet again in a new video with a new simulation. Goodbye till then.